Welcome, everyone. It is my pleasure to introduce today's speaker, who is Rupert Frank from Caltech, and he's going to talk about Lieb-Thirring bounds and other inequalities for orthonormal functions.
All right. Thanks a lot, Polona, for the introduction and for the invitation. It's a pleasure to be here and to give this talk. It's actually things that we worked on a couple of years ago, so it's not the most recent, but I tried to put things a little bit into perspective, and I hope I could arrange them so that you might, or some of you might find them somewhat interesting. I want to start by giving an overview over what the idea is behind these Lieb-Thirring bounds and in which directions we have generalized them in recent years. And then I want to turn to one specific such question. And this is joint work with Julien Sabin from, I think he was at Orsay and now he's at École Polytechnique. All right, so let's get started. So I want to start with really the basic Lieb-Thirring inequality as it was proved in 1975 in work of Lieb and Thirring. And so there are many things in also mathematics and physics that are called uncertainty principle, but not all these inequalities that are written down actually imply the things that physicists like to call the uncertainty principle. So one inequality that does actually imply that is the following Sobolev interpolation inequality. So the setting is the following. We're on Rd. We have a function psi, which is L2 normalized. And we imagine that its gradient squared is integrable, or more precisely that we have a bound. So that means in some sense that the function is localized in momentum space. Right? So because it's if you think about Fourier space, then it's a square integral with respect to the weight p squared. All right. And then the assertion is that the function belongs to an LP space with a p strictly greater than 2. Okay, so we have a function which is L2 normalized, and so it cannot concentrate all its L2 mass at a single point, but it needs to be somehow spread out. Belongs to an LP space with p greater than 2. Okay, so that means what's often meant if a function is localized in momentum space, then it cannot be localized in position space at the same time. Okay, and so the particular expression which is useful in many applications is where you choose this exponent to be that particular value, such that really you have an integral on one side bounded by an integral of the other side. There are no powers involved. But anyway, this is not so important right now. So the physical interpretation is just because of the nature that the wave function is spread out, it cannot be completely concentrated at the nucleus. So imagine you have a hydrogen atom, and then, I mean, classically what would happen is when you minimize an energy, you would just put the point particle exactly at the singularity, and then you would have an energy minus infinity. Now that does not happen in quantum mechanics because the function is spread out, and so it can only feel the Coulomb singularity so and so much. Okay, so that's one of the basic principles in quantum mechanics. That's this uncertainty principle. Now another principle comes when you go to more than one particle. And this is the so-called Polyexclusion principle. And again, physicists would say that functions cannot occupy the same state, whatever that precisely means. So a specific mathematical quantification of this statement is the following inequality. So now we have a whole bunch of functions, either finitely many with some number or right away infinitely many. Okay, and so you assume that these functions are orthogonal to each other in L2 and normalized. Okay, and then what you can do, what the physical quantity of interest is that you sum their squares. That's sort of the density of electrons that you observe. You want to think of these psi n's as the different orbitals. And so this is the overall density of this large number of electrons. And then the inequality says that if we have a bound on the gradient squared of these functions, then actually we have an inequality. It's the same exponent as in the inequality up there, right? So if we have a single function, then the second inequality reduces to the first one. But the main point here is that this inequality holds with a constant that's independent of the number of psi's. In particular, there can be infinitely many. Okay, so how do we think of this? This is really the expression, so let me backtrack a little bit. So the fact that such an inequality can hold with a constant independent of the number of functions comes from orthogonality, obviously, because otherwise I could just take the very same function over and over again. See, that's what we would have on, just this function psi from the first inequality, say, normalize it in L2, and then you have on the sum on the right side, you have something which is proportional to n, where, however, on the left side, you have a sum to a power which is greater than 1, right? So therefore, this would be a contradiction. Okay, so orthogonality is crucial. Now, what this inequality does, however, is that it translates this sort of abstract concept of orthogonality, right, which is just some inner product in Hilbert space, to something very concrete in X space. Right? It says somehow that these functions have to go out of each other's way. Right? The bad thing is if they're all the same and they're all on top of each other. But this abstract orthogonality plus the bound on the gradient forces to them to kind of, think of the functions having disjoint support in X space, right? If the function had disjoint support in X space, then you could just apply the first inequality just at each piece. And so while we don't have, these functions don't have disjoint support, well, this says that in some sense, actually they do. Within the validity of this inequality. Okay, and so I want you to remember from high school chemistry, the atomic orbital model, these pictures where you have these bubbles and where you have the 1s and the 2s, 2p, 3s, 3p, 3d orbitals, right? And then they, as you go higher and higher up, these bubbles go in disjoint directions. That's sort of the thing that is captured here, right? They're not on top of each other, but they grow away from each other. They try to become essentially disjoint in X space. And so if you want to put this into a phrase, then you can say what this says is that orthogonality needs space. That's sort of the principle that's behind this. And you can imagine that this is important to describe some physical properties of matter. In particular, Lieb and Thirring used this in 1975 to prove stability of matter, or rather give a rather direct proof of this original theorem that's due to Dyson and Lenard. Okay, where really this inequality is the main ingredient because of what I explained. So now let me generalize this thing a little bit. I'm pretending here that there is some generality which is perhaps not there really, but at least it might help you to get a little bit an order in how these different inequalities that I will present all fit together in the same framework. So what we have is we have a Hilbert space, okay? And so we have functions psi in this Hilbert space, and then we have a certain operator T that acts on these functions. And what we want is that the space it maps into is an L2 space. And well, this operator is bounded, so therefore we have such an inequality. But now we can ask the questions. Imagine we're given a whole bunch of such functions, which satisfies the same orthonormality conditions as before. Now, is it true that we have an inequality of the following form, where again, we square some, the operator applied to the functions. And then, instead of taking the Q norm of these things, we take the Q over 2 norm of the square sum, or the Q norm of the square function, if you want. And we ask ourselves, can such a sum, which now I'm displaying the number of functions, can such a sum be bounded by n to the sigma, where sigma is a number smaller than Q over 2? Now, where does this Q over 2 come from? Well, that's a trivial bound, right? That just comes from the triangle inequality. If you, take the 2 over Q's root on the left side, apply the triangle inequality, and then for each term in the triangle inequality, apply the inequality above, and recall that the functions are all normalized, then you get exactly n to the Q over 2 here. So that's a trivial thing. That's the argument that does not use orthogonality. That's a situation in the physical picture where all the functions sit on top of each other. The question is, if we have orthogonality now, can we do better than n to the Q over 2? Can we reduce this to a certain power sigma smaller than that? And so while this is a general question, there seems to be no general answer. So, if you give me some operator, there is no way that I can tell you somehow, yes, then you get the power sigma, this and that. But so far, this is like a case-by-case study. We look at the operators and we try to find what we have. And in some situations, we have been able to prove such bounds which beat the triangle inequality and which therefore quantify this effect of orthogonality. So let me give you an example to get back to some concrete problems. And so one of these big theorems that you teach students in harmonic analysis or functional analysis is this fractional integration theorem, or Hardy-Littlewood-Sobolev inequality. Okay, so which says that if you have a function in L2 and then you convolve it with such a kernel, right, x to a power of 1 over x, then this thing belongs to a certain LP space. And which LP space it is, you can figure out by scaling. All right, and so what Lieb back in 1983 proved is that yes, you do have such an inequality for orthonormal functions. Your psi n's are orthonormal, you convolve them, square sum them, and then you take this to a certain power. And then what you get, remember, you want to get here a power which is smaller than the power that you have up there, the power d over d minus 2 alpha. And yes, you do get this. Okay, and in this inequality, the power 1 of n actually is known to be optimal, and that's very so that's one form of stating one of these important theorems in the spectral theory of Schrödinger operators, namely the Zwickel-Lieb-Rosenblum bound, where you estimate the number of negative eigenvalues of a Schrödinger operator through integral of a power of the potential. Okay, so having this bound on the number of eigenvalues of the Schrödinger operator bounded by that, by constant times that, is equivalent to having this inequality valid for all systems of orthonormal functions, psi n. Okay, and so I'm sort of jumping back and forth in this in the next slide between concrete applications, why people are interested in these inequalities, and the inequalities themselves. All right, so let's move on. Let's talk about some things that we've been doing in the past, 6 or 7 years now, where we try to extend these inequalities to further linear operators in harmonic analysis. And these operators, they're all related to restriction phenomena. And so one thing is, for instance, the Strichertz inequality. And the other thing is the Steintomas restriction inequality, or perhaps more precisely, its extension version. So what does this say? So the original Strichertz inequality has the goal of quantifying the phenomenon of dispersion. Okay, so while in an L2 theory, you have a function and then you act on the function with the unitary propagator up there, this is unitary in L2 and therefore just, preserves the L2 norm for all times. But that's somehow not the whole story, because you have this phenomenon of dispersion, right? So as time goes by, well, while the L2 norm is preserved, actually what happens is that this wave spreads out. And that's sort of quantified by the Strichertz inequality by having a dt integral finite. Okay, so to have an integral finite at infinity means that in some sense, the integrand has to go to 0. Okay, so this really says that somehow as time goes on, this wave packet really somehow goes to 0. So what exactly do we do here? So we take the evolution of a single orbital, square sum, and then we raise it to a certain power. We have to integrate first over x, possibly raise to another to a power p divided by q different from 1. In the case p equal to q is allowed. And then you integrate over time. And the original Strichertz inequality is that for one function, this is bounded when the functions are normalized in L2. And our theorem here is that this is bounded by n to a certain power. And you have to believe me that this power that I've written up there is actually a power that beats the triangle inequality. Okay, so you do have this phenomenon again that you have a gain in the number of functions due to orthogonality. And this gain that I quantify here, this power p divided by q plus 1 divided by 2q, you don't have to remember that, but it's an optimal power. So there is actually some heuristics that explain that you can achieve this, right? So I can come up with functions, with a sequence of functions where the left side grows exactly like n to that power. Okay, now once again, this thing is not proved just because it's nice, which it is or is not, depending on how you feel about this, but really because people ask this question for the dynamics of quantum many particle systems, and there this orthogonality condition is natural. That's the fermionic nature of the electrons. And when you want to study this and these large systems, then it's, such inequalities are important. And one is dealing, so to speak, with 10 to the 26 or so electrons, and then really this power makes a difference. You need to get the right power when you want to say something about these realistic systems. Another inequality, at least from a harmonic analysis perspective, has a related flavor, is the Steintomas inequality. All right, so in that inequality, we're given now functions that live on the sphere as d minus 1. And what we're doing is we're computing their Fourier transform. Okay, so really what you should think of these functions as sort of as measures on the sphere and then the Fourier transform of that measure. Okay. And then it's a theorem that these functions belong to LQ for a certain Q which is greater than 2. All right. And once again, so Steintomas proved this inequality for single functions. This inequality does have an extension to several functions. And once again, one can prove this with an optimal power, which in this case happens n to the d over d minus 1. Okay, and once again, there is a motivation behind doing this. And this is now, so far, we've been talking about Schrödinger operators. And I've always thought about self-adjoint Schrödinger operators implicitly. Now, what I'm interested here are Schrödinger operators with complex potentials. Okay, now Schrödinger operators with complex potentials can have their eigenvalues everywhere in the complex plane, and the ones that are particularly difficult are the eigenvalues that accumulate at a positive energy. Okay, and so if you have eigenvalues accumulating at positive energy, that sort of, I mean, tells you, I mean, the Laplacian, right, that's kind of brings in the Fourier transform. The Fourier transform diagonalizes Laplacian. And so at positive eigenvalues, this means that what's important is what happens on this energy shell. And that's exactly where such Fourier restriction theorems, which restrict to such an energy shell, come in. Okay, so this would be a whole different topic of a talk to explain these consequences of these inequalities. I don't want to do that. There's one other thing that I don't want to do, and this is talk about sharp constants. So if you go back to the previous slide, 2 slides ahead, where where you have the Lieb-Thirring inequalities. So this was proved in 1975. We know exactly when these inequalities are valid, because there's a whole range of inequalities. I've only written down the simplest one. But what we don't know is what the optimal constant is here in this inequality. Okay, and so in the last 45 years or so, people have really worked hard in getting constants here, getting good values on these constants. In particular, just to mention one direction here is in 1 and 2 dimensions, it's believed that the same constant that makes the first inequality valid makes the inequality for all functions valid. Okay, so instead of, I mean, the best thing, I mean, here you could take many, many functions, but the best thing for the inequality would be just to take a single function. Now, on the other hand, if you go to 3 dimensions and higher, there's some strange dimensional phenomenon coming in, and then suddenly a completely different scenario is expected to be optimal. But that's a completely open question. I'm just saying this because this is really what motivates a lot of result in this area. When we go back to these more modern inequalities that I've talked about, there you can ask similar questions, right? I mean, there's a natural constant here that comes from just the single inequality of the Strichertz inequality. Strichertz inequalities are, and sharp constants there, are a big topic in the last 5 or 10 years or so. So one might ask, is this the same for the many functions? Or else, again, we have an analog of this many particle scenario. Is this what decides what goes in here? Similar questions about the Steintomas inequality. All right, so let me summarize where we are. I've presented to you so far a couple of inequalities, which all have sort of a similar flavor. There is also a somewhat similar flavor in the proofs, or more precisely, I should say, there's a certain proof technique. And if the original one particle, one function inequality is proved using that technique, then there's a good chance that you can extend these proofs to many functions. Now, not all techniques, not all harmonic analysis techniques that are used to prove single function inequalities are applicable to the many particle settings. In particular, Littlewood-Paley theory, which is really a basic thing in harmonic analysis, seems to have no analog in this multi-particle setting. And I mean, that's of course a big drawback, because when you think about these things, Littlewood-Paley theory is really one of the basic ingredients that are used. Now, you might ask me now, is it just that we don't understand how to generalize this for the many functions, or is it genuinely non-valid? I don't quite know the answer. But for instance, there are, you might have heard about these endpoint Strichertz inequalities due to Kiel and Tau, right? And so the analogs of these inequalities are not valid in the many function settings. So there you do not have an improvement over the trivial triangle inequality. So there are some, it's not like every inequality has such an analog, and which we just need to sit down and work out. but it's really still not really understood which inequalities do and which don't. And there is a certain conjectured range for the Stichhartz inequality. So what I've written down is a smaller range than for the one function Stichhartz inequality. And what goes on outside the range is not clear yet. And in particular, but what we do know is that the range is smaller than for the single function case. Okay, so that's another open problem in this area. Now, while there are certain techniques, more or less, I mean, techniques that you can use to prove these inequalities, what's often harder actually than to prove is to show that these powers in n are optimal. Because you need to come up now really with many functions. I mean, n goes to infinity, and you need to come up with a way to arrange these functions to exactly saturate these inequalities. And in that respect, the inequalities are actually quite different. Now, for the remainder of the talk, I would like to talk about a variant of the Steintomas inequality on Riemannian manifolds. Okay, so the Steintomas inequality, as I tried to explain, for me is intimately related with the Laplacian, right? Just because I have the Laplacian, I diagonalize the Laplacian, and then I have a spectral subspace. Even, I mean, it's perhaps in the continuous spectrum, but something like, and the Steintomas inequality is for me sort of a restriction to that spectral subspace. Now, when you are on Riemannian manifold, then a compact Riemannian manifold, then you have discrete spectrum. And so you need to talk about really honest spectral subspaces. It's a little bit more complicated. So what you need to do is you have to smear out this Steintomas restriction. Not, I mean, you don't integrate exactly over a sphere, but rather over an annular shell. So think of the inequalities that are going to follow as versions where you just have integrated this inequality. I mean, it's not the unit sphere, but say the shell between radius 1 and radius 2. And then actually, I mean, in Euclidean space, we have a scale invariance. So instead of just integrating between 1 and, I mean, if you understand integrating, if you understand the restriction just to one sphere, then you understand it to every sphere. And you can do this integration around every sphere. What I'm saying is now on a Riemannian manifold, there's another parameter in the game, and that's where you center this sphere. So we agreed that the sphere really is a shell now, but it's sort of going out. Okay, and it's normal, I mean, we call the values between which we are integrating lambda squared and lambda plus 1 squared. You'll see that in a second. But what I'm saying is it's a generalization of this inequality, and really it's a generalization of a generalization of this inequality. Anyway, let's be more concrete. And I want to motivate this now in a different way. I mean, the inequality that I was telling you about is going to come. But let's switch gears. So from now on, there is the inequalities before don't play any role anymore. You can, if you can start listening now if you want. And I want to talk about the Laplace-Beltrami operator, and just for the sake of motivation, let's talk about it on S2. Right? That's the simplest case where we can know exactly its spectrum. It consists of eigenvalues at L times L plus 1, and they have each multiplicity 2L plus 1. We denote the corresponding eigenspace by EL, and we ask ourselves, how much can a function in that particular eigenspace be localized? Okay, so it's the functions we're interested in are linear combinations of the YLMs with fixed L. And we're asking about their localization properties essentially as L goes to infinity. Now, of course, what we have to make precise is how do we measure localization? What do we mean by this? And so one way of doing this is we could look at the LQ norm of the functions with some Q greater than 2. Okay, so the functions are normalized in L2 all the time. But now we want to make, we ask ourselves, how big can the LQ norm be? And that question was asked and answered by Zog in 1987. And he showed that in this two-dimensional case, there is a critical exponent q equal to 6. And so, I mean, first of all, the Q norm is bounded in terms of L, the square root of the eigenvalue, to some power. But the point is that this power changes, or the analytic expression for this power changes as Q crosses 6. And that corresponds to two different scenarios of optimality. Namely, when we have a large Q, okay, then in order to maximally localize a function, you take a function that is localized around one of the poles. Okay, and if you follow then the counting, there's a certain length scale L to the -1, that's the size of this neighborhood of the pole where the function is localized. And then there's a size L to the 1/2 that the function has in that ball. Okay, and in terms of spherical harmonics, this corresponds exactly to m equal to 0. Okay, so these functions are within a constant, the most localized functions that you can find in this eigenspace. And the Q norm, just because of this size of where the function is localized and the size of the function in that region, you arrive at a certain expression. And Zog showed that this is the optimal expression. The story is a little bit different when you go to powers Q, which are below 6. In that case, you do not want to localize functions at only a single point, but rather you want to localize them around the equator. Okay, so which is sort of a bigger set. And so it's, again, there's a certain size of this set, L to the -1/2. That's the neighborhood around the equator. So it's, it's still shrinking the set, but it does not shrink in the orthogonal direction. And then there's a certain size that the functions have in that neighborhood. And once again, if you put this into the computation, you find a size for the Q norm, and then Zog proved that this is actually the optimal size for these functions. Okay, and Zog proved this not only in the case of S2, but actually in the terms of any compact manifold in any dimension. And he has certain exponents. 6 is the corresponding exponent for 2 dimensions where this behavior changes. But it's always this dichotomy, because between point localization for large Q and localization on pieces of a geodesic, or pieces which are order 1 in one direction and small in the other directions. All right. So what I wanted to discuss now is the extension of this theorem to the setting of orthonormal functions. Okay, so we have these spaces of functions of dimensions that are increasing. So at eigenvalue L squared, or L times L plus 1, I have 2 L plus 1 functions. There are many functions. And I'm gonna ask myself, how much can a subspace of these subfunctions be localized? Not a single one, but really all functions together in that subspace. So what exactly do I mean? So I'm picking a subspace L in that spectral subspace EL, and I'm taking an orthonormal basis in that, of that subspace. Okay, so I'm picking n functions in that space. And then what I'm looking at is their square sum. This is a quantity that's independent of the choice of the basis. So it really depends on the choice of the subspace in that space of spherical harmonics. And the parameter n is at our disposal. And so Zog would have chosen a single function. And of course, something which is easy I mean, not really easy, but perhaps well known, is when you take all the functions. When you take the full, I mean, the density of the full space of these spherical harmonics or general eigenfunctions. Okay, but we're looking at something in between. So n is a number between 1 and L, and which typically tends to infinity with L, but not as fast as L or 2L plus 1. Okay. And then our goal is, well, again, we look at the Q norm of this square function, or the Q over 2 norm of that density, if you want. And we want to bound this in terms of the two parameters that we have now. One parameter is L, that's the degree of the eigenvalue. And the second parameter is the number of functions that we've chosen. And as I already said, picking one function, we're back in Sorg's regime. Picking all the functions at once, well, in the case of the sphere, that's easy because there's a formula for the sum of these. And what you see is just by rotation invariance, the density then is constant. So in some sense, here you have a complete delocalization. This density is completely flat. And now here's a preview of this theorem that I want to discuss in the remainder, is that there's a bound on this norm. And that bound, again, has two different regimes. There is the regime where Q is greater than 6. This is where for a single function, I would localize around a point. And even for many functions, I still want to localize around a point. It's just that now the region will be larger and larger. And the size of the function will also change. And similarly, there's the other regime where before we localized around the equator, well, we still do that, except that the size and of the region and of the functions change now. And they change depending on these two parameters, L and N. And I mean, without going into these precise details of what this means, I mean, you can read it off right from the way I've written it. The powers here that are independent of Q, these are kind of the size parameters, how big these functions, how big this row is. And the ones with the Q, those give you somehow the volume where these functions are localized. But the point that I try to make is we're similarly, as at this very beginning, this key observation of Lieb and Thirring, that orthogonality needs space, that these functions have to arrange them away from each other. We see that again inside these spaces of spherical harmonics. Okay, it's sort of, they want to go out of each other's way. I mean, we want to localize them, so we want to keep them together. But because of orthogonality, they can't, or when I'm saying orthogonality is that I fix the dimension of the space, right? So they can't be too close together. So therefore they have to grow sideways and also a little bit upwards. Okay. And that's what's sort of quantified here in this regime, where you're much more restricted of how you can choose your functions. And again, the key idea is we see the effect of orthogonality, right? We can beat the power n to the 1/2. Yeah, I've written 1/2 here. We beat the power that we would get by a simple application of triangle inequality. And that says, again, so you cannot manage to localize every function as well as Sorg could localize a single function. Right? I mean, you can localize a finite number of functions in that way by just, I mean, I've explained you what Sorg does, and so you can just put them onto a finite number of points. But when I ask you to look at a number of functions that goes to infinity, then you really need then orthogonality kicks in, and you have to respect the other functions, and you cannot occupy all the space. And our theorem is the powers that we see there are optimal, and optimal in a very, very strong sense. So no matter what dimension you give me, so give me a sequence of NLs. I only ask you that the sequence should go to infinity, right? Because if it's bounded, then I just take the functions of SOG. If also I require that it goes to infinity slower than L, which is clear because otherwise we're sort of in this completely delocalized regime that I described before. But no matter how you grow, so it could be log L, log L, or it could be L divided by log L. Okay, so no matter what you have, you find a subspace which has asymptotically that given dimension NL, and for which you have the reverse bounds. So we really determine the optimal way orthogonality forces a maximal localization on the sphere in a cytospectral cluster. And so now I'm stating this theorem here in somewhat more detail. I'm stating this in a general setting. Let M be a manifold of dimension d greater or equal than 2. And somehow the important word here is really it's without boundary. So to be completely honest, the boundaries we cannot deal with. Now that being said, I mean, SOG can't deal with boundaries in the single function case. So it's no surprise sort of that we cannot do this. There might be some situations when you have a concave boundary that one can say something, but let's ignore boundaries, okay? And it's perfectly fine if you just think about the sphere. All these theorems are interesting on the sphere, and in some sense, spheres are actually the key thing. And so here's the theorem in its complete form. So given these functions psi n, these functions are orthonormal, and they are restricted to lie in a spectral subspace where the energy parameter is between lambda squared and lambda plus 1 squared. Now, before we just took these functions, right? And so we sort of, when you think about occupation numbers, we had, I mean, all the functions we took were occupied and those we didn't take were not occupied. Now, what you can do is you can add some numbers, nu n here, arbitrary numbers. And you want to think of them, I mean, before we thought about these numbers just as zeros or ones. Now, you don't need to do this, and you can put these, I mean, and then you get an inequality, which has the q over 2 norm of the square sum, right? Similar as we want. But now the right side depends on these numbers. So that would just be n to a certain power if you decide to just take zeros or ones. But this theorem is a little bit more general. And then we got, first of all, lambda to the 2sq. So sq, that's SOG's exponent. I told you that there's a transition at a certain value of q. So this number 2 times d plus 1 divided by d minus 1. Above that number, we have localization at a point. Below that number, we have localization along a geodesic. And there's another exponent now coming. That's the 1 over alpha q exponent. Now that's the number, that's the exponent of capital N that we talked about before all the time. Okay? So just, I mean, just think if this is too complicated, just write instead of the sum, just write an n there. And then you get this, so alpha of q, there's a certain power. And the only thing you should remember about this power is that it's the optimal power. Okay, optimal again in the strong sense that whatever dimensions I give you, as long as they go to infinity and that they grow slower than the dimension of the full space, we can come up with functions actually with, we don't need to make use of this freedom of adding non-zero and not one numbers lambda n, such that we have a total of n such functions and we have the reverse inequality. I said it before, for if we take a single function, this we get back to SOG's result, which is valid in this Riemannian setting. And if we take all the functions, So if we take psi n to be an orthonormal basis of E lambda, then we get the pointwise Weil asymptotics of Awakumovich and Levitan that goes back to the 1950s or 1960s. More precisely, I mean, it's not the Weil asymptotics, but it's the key ingredient in their proof of the sharp Weil asymptotic formula. Okay, so this is the regime where the density then is comparable to a constant. It's bounded from above and bounded from below by the same number of two constants. All right, so that was the result. Let me give you a little bit of a flavor of the proof. I mean, I don't know how long this will go now, how long you're willing to stay. I will not go very much longer, but I want to give you at least a little bit of an idea of how one goes about that. And then at the end, so I think there are 3 more slides, I think. I will give you a little bit of an idea of what one does concerning orthogonality, concerning optimality. So, okay, I need the notion of the Shuttle norm of a compact operator. Okay, that's a measure of compactness. And how is that defined? Well, out of a compact operator T, you form a self-adjoint compact operator, T star T. This has eigenvalues, and then you take the alpha over 2 norm of that thing, or, yeah, well, I mean, the square of that norm, okay? And so that measures how fast the eigenvalues go to 0. And then you can write the inequality that looked a little bit complicated on this slide. You can write it in a compressed, oops, what happened now? Can you see my screen now?
Yes, yes, we can.
Okay, somehow my screen disappeared. Anyway, right, okay. So you can write the inequality in a compressed form as saying that a certain Q over 2 norm of a function rho is bounded by a certain Shuttle norm of a certain operator gamma. So what is this operator gamma? Well, what you do is just I mean, these are the psi n's, these are the functions, the orthonormal functions we were talking about. There were these numbers nu n, which I threw in and which I told you, you can think of 0s and 1s if you want. But so you can put them together and form an operator gamma. And so on the right side of the inequality, what we have, right, this little L alpha norm is nothing else than that the Shuttle alpha norm of this operator gamma. On the left side, well, you have something which we like to think of as the density of that operator, which means just, I mean, everything is finite dimensional. Just take the kernel of that operator and evaluate it at the diagonal. And you're taking an Q over 2 norm of that thing. Okay, so that's one way of stating the inequality in a concise form. But not only that, it also gives you an idea of how to prove it. Namely, you can use duality now, right? So in order to compute an LQ over 2 norm, you test against an element in the dual space. And that element in the dual space, that will be W squared. It's somehow because the function is non-negative, the element in the dual space that you test against can be assumed non-negative. So I like to write it as a W squared. Okay, so then just by duality, there's really not much more to it. You build an operator W pi W. Of that operator, you compute the Shuttle alpha prime norm. That's a dual of the Shuttle alpha norm. You bound that by the 2Q over Q minus 1 norm of W squared, which is just a funny way. I mean, I wanted to get a W squared in there. So this is really just the dual norm of LQ over 2 of W squared. Okay. So, and what is pi? Pi is just the projection to the full spectral subspace. Okay, so that's our goal. That's what we have to do, which somehow eliminates our choice of functions. Right before we had this arbitrary many functions floating around. Now we're just saying, take this spectral projector, multiply it from the left and from the right by a function W, and try to get a bound on the rate of its eigenvalues. And in terms of a fixed LR norm of this function W. Now, there are two particular cases where this inequality is very easy to prove. This is the case where Q is equal to 2. Let me, in that case, when you work this out, on the left side, you have just the norm in the sense of bounded operators. And the power that you get there happens to be the 0 power. So all there is to it is that you have the operator W, pi W. Pi is a bounded operator, it's a projection, right? So it has norm 1. And W, you can think as that's the operator of multiplication by W. That's, of course, bounded by the L infinity norm of the function. So that's a completely trivial bound. The other case that I mentioned that is simple is the case where Q is equal to infinity. When Q is equal to infinity, when you look at this Shuttle exponent on the left side, well, that's the trace norm. So the trace norm, since this operator is non-negative, that's really just the trace, which you can write out as an integral over the diagonal. Now you use this Abakumovich-Levitan bound, which says that this projector on the diagonal is bounded by lambda to the d minus 1. And that's it. Then you have the L2 norm of the function left over, and that's a decide bound. So what does this say? If we go back to the inequality, there are the boundary cases, the case Q equal to 2 and the case Q equal to infinity. Those are easy. By complex interpolation, the only thing that we have to do is therefore to deal with this point where the line breaks, right? The special point of SOG. All right, that's what I've written here. So we got now, there's a single point Q, and if you work all the powers out, what you have to do is you have our operator W pi W, got to compute a Shuttle norm of this thing, and got to bound this by a certain power of lambda times the L d plus 1 norm of this function W that acts here as multiplication by the left and multiplication by the right. Now, how does one prove something like this? Well, this is the step where you at least follow partially the one function case. So first of all, you want to smooth out the projection, right? So I mean, in the spectrum, before we had a characteristic function really localizing to this spectral window, when you work with these stuffs, it's always nicer to smoothen out this characteristic function. So that's relatively standard. And once you've smoothed it out, you can use a parametrics for this smoothed out spectral projection. And this parametrics has a very special form, namely, I mean, there's a remainder which we can treat with methods that we've talked about before, but the main term in the parametrics has a very peculiar form. So first of all, there's a certain size, lambda to the d minus 1 over 2, but then more importantly, there's a certain phase. And the phase is e to the I lambda, the Riemannian distance between x and y. It's only interesting when x and y are very close together. Okay, this might remind you of the asymptotics of Bessel functions, right? Because I mean, after all, Bessel functions are the analog of this thing in Euclidean space, and they have asymptotics like e to the I lambda absolute, I mean, just the distance between x minus y. Okay, and perhaps even a sine and a cosine. But here we've only taken one of the two exponentials. And then this is multiplied by a certain amplitude, which is harmless. So it has itself and all its derivatives are nice and order 1. So really what we need to understand are such operators with such phases. And there we get in Theorem that's a standard harmonic analysis. These are oscillatory integrals of exactly such a form. So you have an amplitude, which is unimportant, and then you have a phase. And concerning the phase, you assume a certain non-degeneracy condition. So there's first of all the condition that the rank of this mixed Hessian is full. And then there's a certain condition due to Carlson and Schollin, which I guess I don't want to recall because, I mean, either you know it or you don't, but it's the same condition that we have in the one function case. Okay, I should perhaps emphasize, however, that this is an operator that takes functions defined on R d minus 1 and maps them to functions on Rd. That's again, I mean, a standard thing that one does in this business. And then in some sense, the technical aspect really is to prove a theorem about such oscillatory integrals. So you see that theorem looks pretty much like what we had before. You see, I mean, these, if you again take the lambdas, just either 0 or 1s, then you see the square functions of these oscillatory integral operators applied to psi n. You see a certain power that beats the triangle inequality to be useful, and then you have lambda to a certain power. And again, you can think of this in a dual form, the way we're using this, where you look at these oscillatory integral operators and multiply them by W and talk about their trace ideal properties. So let me say it again. If you have a single function, this thing is just the theorem of Carlson-Schollin and Stein. You can, so that's this thing here, this inequality here for a single function. What you can do is you can dualize this Carlson-Schollin inequality for a single function, and you get equivalently that this operator is bounded. The WT operator is bounded, and it's bounded exactly in terms of these things. The novel thing here is that we say that not only is this operator bounded, but we say that it's compact, and more importantly, we quantify its compactness. We quantify how fast its singular values accumulate at 0. That's the way you can look at this. And actually, the proof of this bound, I mean, even this compactness bound, is not so vastly different from the proof in the single function case, in the sense you still use complex interpolation. So once again, a complex interpolation, but now you change, so to speak, the operator as you go along. I will not talk about this. Okay, this is really, yeah, I mean, this, even though this is the main technical main part of the proof, because as I said before, if you combine this with all we've discussed before, plus a little argument to recover that missing direction, you get back to the spectral cluster theorem. What I want to spend the last 2 minutes about is talk about the proof of optimality, because this is sort of a little bit where you have to get your hands dirty. I mean, you really have to construct these functions. And I remind you what we want to do is that we're given this power between 2 and q. We're giving a sequence of dimensions that goes to infinity, but not as fast as the full dimension of that spectral subspace. And we want to find an orthogonal projection which only lives in that spectral subspace, whose range has dimension n, and such that we have the reverse bound to the one I mentioned before. Okay, so there's the lambda to the 2s, that's the SOG exponent that we talked about. And then there is this, I mean, the sum now has just become again the n, and this was to the power 1 over alpha in our notation. And one can do this in general, but I want to just talk about the proof on S2, which which was our original motivation. And essentially, it's a generalization of this idea of SOC, how to localize these functions. Remember, when Q was large, we localized the functions in a neighborhood of a pole, and that corresponded to the YL0 function. So roughly speaking, what we're doing is we take the YLMs with M very small, and we take all of them. All of as many as we need to take, right? We need to take N functions. I'm writing NL in this case of the sphere instead of N lambda in the general setting, okay? So we have NL functions that we need to take, and we just take the first integers from 0 up to NL. That does not quite work. You need to throw away the first for technical reasons, but morally think of this as just taking the first M values and looking at the corresponding projection. And then I said, when you want to localize functions in a LQ with a small q, q less than 6, then you want to do this around the equator, right? And I said that you do this by taking the YLMs where M now is equal to L. So again, the natural choice would be to just take the last M's. So you take the last NLMs to build the operator. Again, for technical levels, you can't really start counting at L, but it's a little bit more convenient to start at L minus N and go down to L minus 2N, but that's only technical. So you see, we take very explicit spherical harmonics or linear combinations of spherical harmonics, and then you have to start to work. So you evaluate this gadget now on the diagonal, right? So these are just these YLMs evaluated at a point, which in spherical coordinates I write as phi times theta. And then we have to estimate the size of these things because we want the lower bound. And actually, one is able to get such bounds in regions which have exactly the size predicted by the theorem. And the functions are of the size predicted in the theorem. Okay, and if you just plug these size estimates and the amplitude and the support size estimates, if you just plug them into the LQ with 2 norms, then you get the desired reverse bounds. Now, the hard thing is to prove these bounds. Okay, and so the way we do this here in this paper is by a WKB construction. These functions are eigenfunctions of some Legendre or associated Legendre equation. And so we use WKB methods to analyze this ODE. So that gives us both an amplitude and a phase. But unfortunately, that's not quite enough because somehow you have to, so these functions, they have a phase, right? They oscillate in particular. When I say a phase, it's not a complex phase, it's a real phase. It's something like sine or cosine. And so roughly speaking, you want to use the fact that there's a sine squared and a cosine squared. And if you take them together, then this is 1 and not too small. But the point is that the argument of the sine and the argument of the cosine is different as you jump, so I'm talking about 2 adjacent such functions for 2 adjacent m's. The point is that the argument of the sine and the argument of the cosine are too different to just apply a Taylor expansion to say that sine squared plus cosine squared is 1. Okay, the error when I replace the cosine of one argument by the other argument is too large. So there is actually something rather non-trivial that we have to understand concerning how the phases interact with each other and that there are not too many cancellations. And so you do this by using some techniques from exponential sums, from analytic number theory. In particular, there's a very useful inequality due to Kuzmin and Landau that we use here. And we hope that this technique that we use there actually is in general helpful when one deals with such phases of orthonormal functions. But I think I've talked long enough. Thanks a lot for your attention.